Okay, well, let's continue the going through this material on decision analysis and support. I introduced some basic concepts, and now I'm going to continue on thinking more in detail about the decision process and work through the material here that we are covering in this chapter. So let's first talk about supporting decisions, the level of technologies needed to support the three different decision types vary. For structured decisions, uncertainty is minimal. Databases and information systems are able to organize and present information clearly, enabling informed decisions. For semi-structured decisions, however, simply organizing information is not efficient. There are decision support systems, DSS, that are needed to analyze information, fuse information from multiple sources, and process information to discover trends and patterns. Unstructured decisions require the most sophisticated level of technology, expert systems, sometimes called knowledge-based systems. Due to the high level of uncertainty and a lack of historical precedents and knowledge, sophisticated inference is required from these systems to provide knowledge to decision makers. Then we have a formal decision-making process. A structured process for decision-making would be important for system teams to adopt. So what we're showing here is a depiction of a general process. This is similar to what we showed in an earlier figure here, but now we're showing it in a different way of considering this information that provided the concept of a modeling the decision. So the approach that we're showing in this figure is refers to the activities of developing a model of the issue or problem at hand and predicting the outcome of each possible alternative choice available to the decision maker. Developing a model of the decision means creating a model that represents the decision context and environment. If the decision refers to an engineering subsystem trade-off, then the model would be of the subsystem in question. Alternative configurations representing the different choices available would be implemented in the model, and various outcomes would be captured. These are then compared to enable the decision maker to make an informed choice. Of course, models can be quite complex in scope and fidelity. Available resources typically provide the constraint on these two attributes. Engineers tend to desire large scope and high fidelity, while the available resource constraints the feasibility of attaining these two desires. The balance needed is one responsibility of the systems engineer. Determining the balance between what is desired from a technical perspective and what is available from a programmatic perspective is a balance that few people beyond the system engineer are able to strike. Although we have used the term model, it is important to realize that the models come in all shapes and sizes. A spreadsheet can be a model of a decision. A complex digital simulation can also be an appropriate model. What types of model to develop to support decision-making depends on many factors, and we'll list these, and these are discussed in the textbook. One, the decision time frame. How much time does a decision maker have to make the decision? If the answer is not much, then simple models are the only available resource unless more sophisticated models are already developed and ready for use. Resources, funding, personnel, skill level, and facility/equipment are all constraints on one's ability to develop and exercise a model to support decisions. 3, problem scope. Clearly, simple decisions do not need complicated models. Complex decisions generally do. The scope of the problem will, in some respect, dictate the scope and fidelity of the model required. Problem scope itself has many factors as well, range of influence of the decision, number and types of stakeholders, number and complexities of entities involved in the decision space, and political constraints. 4, the level of uncertainty in the information needed will also affect the model type. If large uncertainties exist, some representation of probabilistic reasoning must be included in the model. 5, stakeholder objectives and values. Decisions are subjective by nature, even with objective data to support them. Stakeholders have values that will affect the decisions and in turn be affected by the decision. The systems engineer must determine how values will be represented. Some may and should be represented within the model. Others can and should be represented outside of the model. Keep in mind that a large part of stakeholders' values involve their risk tolerance. Individuals and organizations have different tolerances for risk. The engineer will need to determine whether risk tolerance is embedded within the model or handled separately. In summary, modeling is a powerful strategy for dealing with decisions in the face of complexity and uncertainty. In broad terms, modeling is used to focus on particular key attributes of a complex system and to illuminate their behavior and relationships apart from less important system characteristics. The objective is to reveal critical system issues by stripping away properties that are not immediately concerned with issues under consideration. Next, we'll discuss modeling throughout the system development. So models have been referred to and illustrated throughout this book. The purpose of the next 3 sections in this chapter and part of this lecture is to provide a more organized and expanded picture of the use of modeling tools in support of system engineering decision-making and related activities. This discussion is intended to be a broad overview with the goal of providing an awareness of the importance of modeling to the successful practice of system engineering. The material is necessarily limited to a few selected examples to illustrate the most common forms of modeling. Further study of relevant modeling techniques is strongly recommended. Specifically, the next 3 sections will describe 3 concepts. Modeling, which describes a number of the most commonly used static representations employed in system development. Many of these can be directly used by system engineers, especially during the conceptual stage of development, and are worth the effort of becoming familiar with their usage. Next, there's simulation, which discusses several types of dynamic system representations used in various stages of system development. System engineers should be knowledgeable with the uses, value, and limitations of the simulations relevant to the system functional behavior and should actively participate in the planning and management of the development of such transitions. Finally, there's trade-off analysis, which describes a modeling approach for the analysis of alternatives, AOA. System engineers should be expert in the use of trade-off analysis and know how to critically evaluate analyses performed by others. So this section also emphasizes the care that must be taken in interpreting the results of analyses based on various models of reality. Next, we'll have a couple of slides that highlight some of the details for modeling for decisions. So as discussed above, we use models as a prime means of coping with complexity to help in managing the large cost of developing, building, and testing complex systems. In this vein, a model has been defined as a physical, mathematical, or otherwise logical representation of system entry, phenomenon, or process. We use models to represent systems or parts thereof so we can examine their behavior under certain conditions. After observing the model's behavior within a range of conditions and using those results as an estimate of the system's behavior, we can make intelligent decisions on systems development, production, and deployment. Furthermore, we can represent processes, both technical and business, via models to understand the potential impacts of implementing those processes with various environments and conditions. Again, we gain insight from the model's behavior to enable us to make a more informed decision. Models only provide us with a representation of a system, its environment, and the business and technical processes surrounding that system's usage. The results of modeling provide only estimates of the system's behavior. Therefore, modeling is just one of 4 principal decision aids, along with simulation, analysis, and experimentation. In many cases, no technique is sufficient to reduce the uncertainty necessary to make, quote, good decisions. Well, let's get into the types of models. A model of a system can be thought of as a simplified representation or abstraction of reality used to mimic the appearance or behavior of a system or system element. There is no universal standard classification of models. The one we shall use here was coined by Blanchard and Fabrici, who defined the following categories. Schematic models, and so this is what we're showing here on this slide, are diagrams or charts representing a system element or process. An example is an organization chart or data flow diagram. That this category is also referred to as descriptive model, and we'll get into the next two we'll show on the following slide. The mathematical model, it uses mathematical notation to represent a relationship or function. Examples are Newton's law of motion, statistical distributions, and differential equation modeling a system's dynamics. And then there's the physical models that directly reflect some of or most of the physical characteristics of the actual system or system element under study. They may be scale models of vehicles such as airplanes or boats, or full-scale mock-ups such as the front section of an automobile undergoing crash test. Some cases, the physical model may be an actual part of a real system, as in the previous example, or an aircraft landing gear assembly undergoing drop tests. A globe of the Earth showing the location of the continents and oceans is another example, as it is a ball and stick model of the structure of a molecule. Prototypes are also classified as physical models. So these 3 categories of models are listed in the general order of increasing reality and decreasing abstraction, beginning with a system context diagram and ending with a production prototype. The category of analog models, which are usually physical but not geometrically equivalent, can be categorized in the physical model category. Well, let's get into some more details. So the schematic model, the schematic models are essential means of communication and system engineering. As in all engineering disciplines, they are used to convey relationships in diagrammic form using commonly used symbology. Mechanical drawings or sketches model the components being designed, circuit diagrams and schematic models the design of the electronic product. Previously, we described model-based system engineering as a computer-based approach to illustrate the system or its components. Schematic models are indispensable as a means for communication because they are easy and quickly drawn and changed when necessary. However, they are also the most abstract, containing a very limited view of a system or one of its elements. Hence, there is a risk of misinterpretation that must be reduced by specifying the means of any non-standard and non-obvious terminology. Several types of schematics models are briefly described in some of the material that we'll cover next. There's also cartoons. While not typically a system engineering tool, cartoons are a form of a pictorial model that illustrates some of the model's objects distinguishing characteristics. First, it is a simplified depiction of the subject, often in an extreme degree. Second, it is emphasized and accentuates selected feature, usually by exaggeration to convey a particular idea. And all the way back in chapter 1, we introduce this idea and having a visual statement concerning the needs for a systems engineering better than the words alone can convey. So a picture is worth 1,000 words. You've probably heard that axiom. An illustration of a system concept of operation may well contain a cartoon of an operational scenario. There's architectural models, a familiar example of the use of modeling in the design of complex products is that employed by the architect for the construction of a home. Given a customer who intends to buy a house to his or her own requirements, an architect is usually hired to translate the customer's desires into plans and specifications that will instruct the builder exactly what to build and to a large extent how. In this instance, the architect serves as the quote home systems engineer with the responsibility to design a home that balances the desires of the homeowner for utility and aesthetics with the constraints of affordability, schedule, and local building codes. The architect begins with several sketches based on conversations with the customer, during which the architect seeks to explore and solidify the latter general expectations of size and shape. These are pictorial models focused mainly on exterior appearance and orientation on the site. At the same time, the architect sketches a number of alternative floor plans to help the customer decide on the total size and appropriate room arrangements. If the customer decides to visualize what the house would more nearly look like, the architect may have a scale model made from wood or cardboard. This would be classified as a physical model resembling the shape of the proposed house. For homes with complex roof lines or unusual shapes, such a model may be a good investment. The above models are used to communicate design information between the customer and the architect, used in the form most understandable to the customer. The actual construction of the home is done by a number of specialists, as in the building of any complex system. There are carpenters, plumbers, electricians, masons, and so on, who must work from much more specific and detailed information that they can understand and implement what appropriate building with the appropriate building materials. This information is contained in drawings and specifications such as wiring layouts, air conditioning routes, plumbing fixtures, and the like. The drawings are models drawn to scale and dimensions using special industry standard symbols for electrical, plumbing, and other fixtures. This type of model represents physical features, as do the pictorials of the house, but it's more abstract in the use of symbols in place of pictures of components. The model serves to communicate detailed design information to the builders. Well, let's explore some more details of the two other categories, the mathematical models and the physical models. So first, for the mathematical models, they are used to express system functionality and dependencies in the language of mathematics. They are most useful where system elements can be isolated for purposes of analysis and where their primary behavior can be represented by well-understood mathematical constructs. The process being modeled contains random variables. Simulation is likely to be a preferable approach. An important advantage of mathematical models is that they are widely understood. Their results have inherent credibility, providing that the approximations made can be shown to be of secondary importance. Mathematical models include a variety of forms that represent deterministic, that is, not random functions or processes. Equations, graphs, and spreadsheets, when applied to a specific system element or process, are common examples. There's also approximate calculations. This needs to be considered. So approximate calculations represent the use of mathematical models, which are abstract representations of selected functions, functional characteristics of the system elements being studied. Such models capture the dominant variables that determine the main features of the outcome, omitting higher order effects that would unduly complicate the mathematics. Thus, they facilitate the understanding of the primary functionality of the system element. As with any model, the results of appropriate approximate calculations must be interpreted with full knowledge that of the limitations due to the emissions of variables that may be significant. If the, quote, sanity check deviates significantly from the results being checked, the approximation and other assumptions should be examined before questioning the original result. In developing the skill to use approximate calculations, the system engineer must make the judgment as to how far to go into the technical fundamentals in each specific case. One alternative is to be satisfied with a review of the designers who made the original analysis. Another is to ask a staff expert in the discipline to make an independent check. A third is to apply the system engineer's own knowledge, augment it by reference to a handbook or text, and carry out the appropriate calculations personally. The appropriate choice among these alternatives is, of course, situation dependent. However, it is advisable that in selected critical technical areas, the system engineer becomes sufficiently familiar with the fundamentals to feel comfortable in making independent judgments. Developing such skills as part of the system engineer's special role of integrating multidisciplinary efforts, assessing system risk, and deciding the areas that require analysis, development, or experimentation. Plus, there's elementary relationships. In every field of engineering and physics, there are some elementary relationships which the system engineer should be aware of or familiar. Newton's law are applicable in a vehicular system. In the case of structural elements under stress, is often used to refer to relationships involving strength and elasticity properties of beams, cylinders, and other simple structures. With electronic components, the system engineer should be familiar with the elementary properties of electronic circuits. There are rules of thumb in most technical fields, which are usually based on elementary mathematical relationships. Plus, there's statistical distributions. Every engineer is familiar with the Gaussian, that is, normal distribution function characteristics of a random noise and other simple natural effects. Some other distribution functions that are of interest include the Rayleigh distribution, which is valuable in analyzing signal returns from radar clutter, the Poisson distribution, the exponential distribution, and the binomial distribution. All of these obey simple mathematical equations. Plus, there's graphs, models representing empirical relationships that do not correspond to explicit mathematical equations are usually depicted by graphs. Such models are usually used to communicate qualitative concepts, although test data plotted in the form of graph can show a quantitative relationship. Bar charts, such as one showing the variations in production by month or cost of alternative products, are also models that serve to communicate relationships in a more effective manner than by a list of numbers. Okay, so that's a detailed discussion on the mathematical models, but now let's talk about the physical models. Physical models directly reflect some or most of the physical characteristics of an actual system or system element under study. In that sense, they are the least abstract and therefore most easily understood type of modeling. Physical models, however, are by definition simplifications of the modeled articles. They may embody only a part of the total product. They may be scaled down versions of developmental prototypes. Such models have multiple uses throughout the development lifecycle, as will be illustrated by the examples that we'll describe next. So that leads us into scale models and other types of things. So scale models are usually small scale versions of a building, vehicle, or other system, often used to represent the external appearance of a product. An example of the engineering use of scaled models is the testing of a model of an air vehicle in a wind tunnel or a submersible in a water tunnel or totem. We have mock-ups. So these are full-scale versions of vehicles, parts of a building, or other structures that are used in later stages of development of a system containing accommodations for operations and other personnel. These provide realistic representations of human systems interfaces to validate or possibly modify their designs prior to detailed design of the interfaces. Then we have prototypes, a key to success in the construction and testing of development engineering and product prototyping as appropriate to a system in hand. These also represent physical models of the system, although they possess most of the properties of the operational system. However, strictly speaking, they are still models. Computer-based tools are being increasingly used in place of physical models, such as mock-ups and even prototypes. Such tools can detect physical interferences and permit many engineering tasks formerly done with physical models to be accomplished with computer models. Then we have human factors models. So human factors models can be used to evaluate how well the human operator can interface with the intended system concept. Some considerations that human system integration, HSI, with system acquisition can include operator workload, decision-making, training, staffing, safety, displays and controls for the operator, displays, alerts, communication, procedures, biomechanics, documentation, and environment. Modeling the operator and evaluating how they interact with the system can uncover areas for improvement within the system design. Another model related to human factors include task analysis and functional allocation. The task analysis decomposes the task into specific elements that can take energy or time to conduct. Analysis of this may be performed with a model in order to analyze the end-to-end flow of elements and identify elements that take longer or more resources. Identification of these key points may also require additional analysis to determine why operators would act in a certain way based on the information presented. Functional allocation can allocate the system functions to available resources, people, systems, tools, etc. By focusing on the human contributions, we will be able to analyze where sufficient resources are provided to task and where additional resources are needed. This again would call for some models to help the engineer to properly evaluate what the task can be performed in such a manner to satisfy the system's objectives. Next, we'll have a couple of slides that will be focusing on simulation. So system simulation is a general type of modeling that deals with the dynamic behavior of a system or its components. It uses a numerical computation technique for conducting experiments with a software model of a physical system, function, or process. Because simulation can embody the physical features of the system, it is inherently less abstract than many forms of modeling discussed in the previous section. On the other hand, the development of a simulation can be a task of considerable magnitude. In the development of new complex systems, simulations are used at nearly every step of the way. In the early phases, the characteristics of the system have not yet been determined and can only be explored by modeling and simulation. In later phases, estimates of the dynamic behavior can usually be obtained earlier and more economically by using simulations that are conducting tests with hardware and prototypes. Even when engineering prototypes are available, field tests can be augmented by using simulations to explore system behavior under a greater variety of conditions. Simulations are also used extensively to generate synthetic system environments inputs for testing purposes. Thus, in every phase of system development, simulations must be considered as potential development tools. So the textbook refers to a book on simulation modeling analysis. And so you can see the textbook for that reference, but talking about it, the authors of that book differentiates the static from dynamic simulations, deterministic from stochastic, and discrete from continuous. For the purpose of relating simulation to their application to system engineering, for this section, we'll group the simulations into 4 categories: operational, physical, environmental, and virtual reality simulations. Of all of these are either wholly or partially software-based because of the versatility of software to perform an almost infinite variety of functions. Computer-based tools also perform simulations at a component or subcomponent level, which will be referred to as an engineering simulation. So let's discuss these individually. So first of all, operational simulation. In system development, operational simulations are primarily used to conceptualize things in the development stage so it's used in the conceptual development stage to help define operational and performance requirements, explore alternative system concepts, and to help select a preferred concept. They are dynamic, stochastic, and discrete event simulations. This category includes simulations of operational systems capable of exploring a wide range of scenarios as well as system variants. Next, we have games. The domain of analyzing operational mission areas is known as operational analysis. This field seeks to study an operational situations characteristic of a type of commerce, warfare, or other broad activity, and to develop strategies that are most suitable to achieve successful results. An important tool of operations analysis is the use of games to evaluate experimentally the use of different operational approaches. The military is one of the organizations that rely on games called war games to explore operational considerations. Computer-aided games are examples of operational simulations involving people who control a simulated system, say a blue team, in engagement with a simulated adversary, say a red team, with referees observing both sides of the action and evaluating the result. So they would be a white team. In business games, the 2 sides represents competitors. In military games, the 2 teams represents adversaries. The behavior of the systems involved in a game is usually based on that of existing operational systems, with such extensions as may be expected to be possible in the next generation of the systems. These may be implemented by variable parameters to explore the effect of different system features on their operational capabilities. Gaming has several benefits. First, it enables the participants to gain a clear understanding of the operational factors involved in various missions, as well as of their interactions with different features of the system, which translates to experience in operational decision-making. Second, by varying key system features, the participants can explore systems improvements that may be expected to enhance their effectiveness. Third, through variation in operational strategy, it may be possible to develop improved operational processes, procedures, and methods. Fourth, analyses of the game results may provide a basis for developing a more clearly stated and prioritized set of operational requirements for an improved system than could be derived otherwise. Commercial games are utilized by large corporations to identify and assess business strategies over a single and multiple business cycles within a set of plausible economic scenarios. Though these games do not typically predict technological breakthroughs, they can identify breakthroughs, technologies that could lead to paradigm shifts in the industry. The military services conduct a variety of games for multiple purposes, such as assessing a new system within a combat situation, analyzing a new concept for transporting people and materials, or evaluating a new technology to detect stealth stealthy targets. These games are facilitated by large screen displays and a bank of computers. And geographic displays are realistic, derived from detailed maps of the global available on the internet and from military sources. Teams are led by officers, but include civilians engaged in defense programs. A complex war game may last from a day to several weeks. The experience is highly enlightening to both military and civilian participants. Short of actual operational experience, such war games are the best means for acquiring an appreciation of the operational environment and mission needs, which are important ingredients in system engineering. Lastly, government organizations and alliances conduct geopolitical games to assess international engagement strategies. These types of games tend to be complex as the dimensions of interactions can become quite large. For example, understanding national reactions to a country's political action involves diplomatic intelligence, military, and economic ramifications, known by the acronym DIME. Also, because interactions are complex, standards simulations types may not be adequate to capture the realm of action that a nation might take. Therefore, sophisticated simulations are developed specifically to model various components of a national entity. These components are known as agents. Then we have system effectiveness simulations. During the concept exploration and concept definition phases of system development, the effort is focused on the comparative evaluation of different system capabilities and architectures. The objective is first to determine the appropriate system performance requirements and then to select a preferred system concept to serve as the basis for development. A principal vehicle for making these decisions is the use of computer system effectiveness simulations, especially in the critical activity of selecting your preferred system concept during concept definition. At this early point in the system lifecycle, there is neither time nor resources to build and test all elements of the system. Further, a well-designed simulation can be used to support the claimed superiority of the system concept recommended to the customer. Modern computer display techniques can present system operation in realistic scenarios. The design of a simulation of a complex system that is capable of providing a basis for comparing the effectiveness of candidate concepts is a prime systems engineering task. The simulation itself is likely to be complex in order to reflect the critical performance factors. The evaluation of system performance also requires the design and construction of a simulation of the operational environment that realistically challenges the operational system's capabilities. Both need to be variable to explore different operational scenarios, such as different system features. There's also mission simulation. The objective of the simulation refers to a mission simulation is focused on the development of operational modes of systems rather than on the development of a system themselves. Examples of such simulations include the conduct of air traffic control, the optimum trajectories of space missions, automobile traffic management, and other complex operations. For example, space missions to explore planets, asteroids, and comets are preceded by exhaustive simulations of the launch, orbital mechanics, terminal maneuvers, instrument operations, and other vital functions that must be designed into the spacecraft and mission control procedures. Before design begins, an analytical foundation using simulation techniques is developed. Such simulation models the vehicles and their static and dynamic characteristics, the information available from various sensors and significant features of the environment, and if appropriate, present these items to the system operator's situation displays, mimicking what would be seen in real operations. The simulations can be varied to present a variety of possible scenarios covering the range of expected operational situations. Operators may conduct what-if experiments to determine the best solution, such as a set of rules, a safe route, an optimum strategy, or whatever the operational requirements call for. Some applications of simulations may include the transportation sector. An initial concept is proposed to add capacity to freeways and exits, so the engineers develop a model to evaluate individual driver operations and behavior to the new concept in order to decide whether the concept is feasible or not. Additional capability may be evaluated that include intelligent transportation systems, where wireless communication between vehicle and ground stations can influence traffic flow, work zones, and future vehicle communication features. Well, continuing on, let's talk about physical simulations. And so physical simulation models the physical behavior of system elements. These are primarily used in system development during the engineering development stage to support systems engineering design. They permit the conduct of simulated experiments that can answer many questions regarding the fabrication and testing of critical components. They are dynamic, deterministic, and continuous. The design of all high-performance vehicles, land, sea, air, or space, depend critically on the use of physical simulations. Simulations enable the analyst and designer to represent the equations of motion of the vehicle, the action of external forces, such as lift and drag, and the action of controls, whether manual or automated. As many experiments as may be necessary to study the effects of varying conditions or design parameters may be conducted. Without such tools, the development of modern aircraft, missiles, and spacecraft would not have been practical. Physical simulations do not eliminate the need for exhaustive testing, but they are capable of studying a great variety of situations and of eliminating all but a few alternative designs. The saving in the development time can be enormous. So let's think in terms of examples: aircrafts, automobiles, space vehicles, and healthcare. Few technical problems are as complicated as the design of high-speed aircraft. The aerodynamic forces are quite nonlinear and change drastically in going between subsonic and supersonic regimes. The stresses of airplane structures can be extremely high, resulting in flexure of wings and control surfaces. They are flow interfaces, effects between the wings and tail structures that depend sharply on attitude, speed, and flight attitude. Simulation permits all of these forces and effects to be realistically represented in 6 degrees of freedom models, 3 positions, and 3 rotation coordinates. The basic motions of an automobile are, of course, far simpler than those of an aircraft. However, modern automobiles possess features that call on very sophisticated dynamic analysis. The control dynamics of an anti-lock brakes are complex and critical, as are those of traction control devices. The action of airbag deployment device is even more critical and sensitive. Being intimately associated with passenger safety, these devices must be reliable under all expected conditions. Here again, simulation is an essential tool. Without modern simulation, there would be no space program as we know it. The task of building a spacecraft and booster assembly that can execute several burns to put the spacecraft into orbit, which can survive launch, deploy solar panels and antennae, control its attitude for reasons of illumination, observation, or communication, and perform a series of experiments in space would simply be impossible without a variety of simulations. The Apollo program would never have been attempted, much less succeeded, if the power of computer simulation had not been available, and certainly not one of the most dramatic examples of simulation which brought Apollo 13 safely home after an explosion in the oxygen generating system, which nearly crippled it fatally. The International Space Station program achieved remarkable sustainability as each mission was simulated and rehearsed to near perfection. The healthcare industry uses physical simulation in numerous aspects of their job. Medical simulation mannequins are lifelike representations of humans that students can practice procedures and record data based on their actions. The simulations can also respond based on the student's actions, such as having seizures, bleeding, and realistic sounds to provide real-time feedback. Other simulations include high-fidelity surgery for training special operation medics. Then there's hardware in the loop simulation, HWIL. This is a form of physical simulation in which system hardware is coupled with a computer-driven simulation. An example of such a simulation is a missile homing device facility. For realistic experiments of the homing dynamics, such a facility is equipped with microwave-absorbing materials, movable radiation sources, and actual heat-seeking and actual seeker hardware. This constitutes a dynamic hardware in the loop, HWIL simulation, which realistically represents a complex environment. Some examples of hardware in the loop may include the automotive industry, where various car components may be hooked up to a simulation to evaluate their capability. Some examples may include car procedures, car batteries, electrical loads, and data communications within the car. By using prototype components, designers can determine if the requirements are satisfied and how much capacity, such as electrical power, resides within the entire vehicle as additional components are added. Then we have engineering simulation. At the component and subcomponent level, there are engineering tools that are extensions of mathematical models, which were described in the previous sections. These are primarily used to design specialists, but their capabilities and limitations need to be understood by a system engineer in order to understand their proper application. Electronic circuit design is no longer done by cut and try methods using breadboards. Simulators can be used to design the required functionality, tested and modified until the desired performance is obtained. Tools exist that can automatically document and produce a hardware version of the circuit. Similarly, the structural analysis of complex structures, such as building bridges, can be done with the aid of simulation tools. This type of simulation can accommodate the great number of complicated interactions among the mechanical elements that make up the structure, which are impractical to accomplish by analysis and testing. Then there's environmental simulation. Environmental simulations are primarily used in system development during engineering test and evaluation. They are a form of physical simulation in which the simulation is not of the system, but of the elements of the system's environment. The majority of such simulations are dynamic, deterministic, and discrete events. This category is intended to include simulation of usually hazardous operational environments that are difficult or unduly expensive to provide the validating the design of systems or system elements, or that are needed to support system operation. I'll list a couple examples here: mechanical stress tests, system or system elements that are designed to survive harsh environments during their operational life, such as missiles, aircraft systems, spacecraft, and so on, need to be subjected to stresses, simulating such conditions. This is customarily done with mechanical shake tables, vibrators, and shock tests. Then we have crash tests. These are used to meet safety standards. Automobile manufacturers subject their products to crash tests where the automobile body is sacrificed to obtain data on the extent to which its structural features lessen the injuries suffered by the occupants. It is done by use of simulated human occupants equipped with extensive instrumentation that measure the severity of the blow resulting from the impact. The entire test and test analysis are usually computer driven. And finally, we have wind tunnel testing and the development of air vehicles. An indispensable tool is the aerodynamics wind tunnel. Even through modern computer programs can model the forces of fluid flow on flying bodies, the complexity of the behavior, especially near the velocity of sound and interactions between different body surfaces, often require extensive testing in facilities that produce controlled airflow conditions, impinging on models of aerodynamic bodies or components. In such facilities, the aerodynamic models is mounted on a fixture that measures force along all components and is computer controlled to vary the model angle of attack, control surface deflection, and other parameters, and to record all data for subsequent analysis. As noted in this discussion of scale models, analogous simulations are used in the development of the hulls and steering controls of surface vehicles and submersibles using water tunnels and tow tanks. Well, let's talk about virtual reality simulation. We'll focus on that and a couple other things, but we have a picture here of showing a virtual reality simulation. So the power of modern computers has made it practical to generate a three-dimensional visual environment of a viewer that can respond to the observer's actual or simulated position and viewing direction in real time. This is accomplished by having all the coordinates of the environment in the database, recomputing the way it would appear to the viewer from his or her instantaneous position and angle of sight, and projecting it on a screen or other display device, usually mounted in the viewer's headset. Some examples of this application, virtual reality simulations, are discussed next. So spatial simulations, a spatial virtual reality simulation is often used when it's important to visualize the interior of enclosed spaces and the connecting exits and entries of those spaces. Computer programs exist that permit the rapid design of these spaces and the interior furnishings. A virtual reality feature makes it possible for an observer to, quote, walk through the spaces in any direction. This type of model can be used for preliminary design of homes, buildings, control centers, storage spaces, parts of ships, and even factory layouts. An auxiliary feature of this type of computer model is the ability to print out depictions in either two-dimensional or three-dimensional forms, including labels and dimensions. Spatial virtual simulations require the input to a computer of a detailed three-dimensional description of the space and its contents. Also, the viewing position is input into the simulation either from sensors in the observer's headset or directed with a joystick, mouse, or other input devices. The virtual image is computed in real time and projected either to the observer's headset or a display screen. So, like I said, we're showing in this figure the relationship between the coordinates of two sides of a room with a bookcase on a wall and a window on the other, and a chair in the corner, and a computer-generated image of how an observer facing the corner would see it. So virtual reality simulations can be applicable to many domains. Agricultural applications can evaluate how well crop yields can be influenced by fertilization techniques, environmental conditions, and use of different systems. Civil engineering can augment their education with computer-aided design, CAD, to assist with construction and rehabilitation projects in order to assist with project planning before moving on site. Transportation applications can evaluate transportation planning, pedestrian movement, and bicycle vehicle interaction and flow. There's video games. Commercial video games present the player with a dynamic scenario with moving figures and scenery that respond to the player's commands. And many games that display is fashioned in such a way that the player has the feeling of being inside the scene of the action rather than a spectator. There's battlefield simulations. A soldier on a battlefield usually has an extremely restricted vision of the surrounding enemy position, other forces, and so on. Military departments are actively seeking ways to extend the soldier's view and knowledge by integrating the local picture with situation information received from other sources through communication links. Virtual reality techniques are expected to be one of the key methods of achieving these objectives of situational awareness. Then there's the development of system simulations, as may be inferred from this section. The several major simulations that must be constructed to support the development of a complex system are complex in their own right. System effectiveness simulations have to not only simulate the system functionality, but also realistically simulate the system environment. Furthermore, they have to be designed so that their critical components may be varied to explore the performance of the alternative configurations. Major new programs, the use of various simulations may well account for a substantial portion of the total cost of the system development. Further, the decisions on the proper balance between simulation fidelity and complexity requires a thorough understanding of the critical issues in system design, technical and program risk, and the necessary timing for key decisions. In the absence of careful analysis and planning, the fidelity of simulations is likely to be over-specified. In an effort to prevent omissions of key parameters, the result of over-ambitious fidelity is the extension of project schedules and exceeding of cost goals. For these reasons, the planning and manufacturing of the system simulation effort should be an integral part of the system engineering and be reflected in management planning. Often the most effective way to keep a large simulation software development within bounds is to use iterative prototyping. In this instance, the simulated system architect is organized as a central structure that performs the basic operation, which is coupled to a set of separable software modules representing the principal system operational modes. This permits the simulation to be brought to limited operation quickly, with the secondary functions added as time and effort are available. Then there's simulation verification and validation. Because simulations serve as an essential and critical function in the decision making during system development, it is necessary that their results represent valid conclusions regarding the predicted behavior of the system and its key elements. To meet this criteria, it must be determined that they accurately represent the developer's conceptual description and specification, that is, verification, and are accurate representations of the real world to the extent required by their intended use, validation. The verification and validation of key simulations must therefore be an integral part of the total system development effort, again, under the direction of system engineering. In the case of new system effectiveness simulations, which are usually complex, it is advisable to examine the results for an existing, that is, predecessor system whose effectiveness has been previously analyzed. Another useful comparison is the operation of an older version of the simulation, if one exists. Every simulation that significantly contributes to a system development should also be documented to the extent necessary to describe its objectives, performance, specifications, architecture, concept of operation, and user modes. A maintenance manual and user guide should also be provided. So the above actions are sometimes neglected to meet schedule and in competition with other activities. However, while simulation are not usually project deliverables, they should be treated with equal management attention because of their critical role in the success of the development. Even though a simulation has been verified and validated, it's important to remember that it is necessarily only a model, that is a simplification and approximation to reality. Thus, there is no such thing as an absolutely validated simulation. In particular, it should only be used for the prescribed application for which it had been tested. It is the responsibility of system engineering to circumscribe the range of valid applications of a given simulation and avoid unwarranted reliance on the accuracy of its results. Despite these cautions, simulations are absolutely indispensable tools in the development of complex systems.